Hi, in this video I'm going to do a deep dive on the Archai neural architecture search and how to set up your Azure ML workspace to run these jobs in the cloud. First you'll want to clone the repository, then go into the face segmentation task. There's a bunch of README information here that's handy that will tell you how this works. As you saw in the earlier video, the search script will run a local search for the best possible model, including doing partial training on the same machine. The AML script will set up the search to run on Azure ML. Let's load this up into VS Code and take a look. Search.py is the one that kicks off an actual Archai neural architecture search. With one of these search algorithms, we're going to use the evolution Pareto search. All of these come from the Archai Python module. You can install Archai in your local Conda environment using this command line, which you'll see in the README instructions. The AML Python script assumes that you have some environment variables, which are referenced in your AML search configuration file right here for a Azure storage account, a subscription, and the resource group for and the name of a Azure ML workspace. So I have the Azure ML workspace set up already. It's easy to create a new workspace. You can just click the Create Workspace button. And I have a storage account set up already. I'm going to use this one. So I have my environment variables configured so that these variables here are defined. This AML search configuration also defines what kind of search space, the parameters on that search space, what search algorithm to use, evolution Pareto with some parameters on that. And it's also defining Snapdragon target for doing inference testing on Snapdragon hardware. That inference test will produce a mean inference time as a key in the storage table. It also configures some training parameters and the key that's produced by partial training, which is a validation IOU metric. And then it defines these Azure ML parameters, including the CPU cluster to use, the training cluster to use, which is a GPU cluster, and the Conda environment needed to run all of this in Azure ML. So when you run aml.py, it's going to go ahead and set up all of these Azure ML resources. And you can see that it loads that configuration and gets all those parameters that are resolved. It creates a conda.yaml file. It creates an Azure ML client so that we can create the CPU cluster and the GPU cluster. It can create the Conda environment from our conda.yaml based on the Azure ML image here that we're referencing. So we're adding the Conda environment on top of that image. Azure ML takes care of creating a Docker image that contains all of these things for us. It also registers our Azure storage account blob store with Azure ML so that Azure ML can find our blob store, and that's done here, both for the dataset and for the models. It then configures our Azure table, which is used to coordinate all of these remote activities, both for the dataset and for the models. It then creates an Azure ML pipeline that launches a job that prepares our dataset, unzipping the dataset from GitHub and putting it into our Azure Blob Store, and sets up a search component to kick off the Azure ML search job. So this component, if we jump to it, is defined here using the Azure ML command API, where it's going to launch the search.py, which is the same script that you would launch if you ran the search locally. It has some fixed arguments, the seed, timeout, and the configuration. And it has some parameterized arguments, which is where's the data set and where to store our output. The data preparation component is similar. It's actually simpler. There's a data prep Python script here with an output, which is a mounted Azure Blob Store. So when we run all of this, it'll create that pipeline and then open it in the web browser. And that's when you'll see a pipeline that looks like this with data preparation and the search job running. Remember from the previous video, we have an Azure ML training pipeline that's going to happen. We have these blob stores and tables that are set up in Azure already, and we have remote device inference testing. We're going to do all of that, and I'm going to show you how to set that up. This README shows how the remote inference testing works. It's actually going to create on a Linux machine various instances of a runner Python script, which is going to talk to Qualcomm devices over USB. The Qualcomm device that we've tested this with is the Snapdragon 888 dev kit, which is basically what you would find in a modern Android phone. We're also going to set up a Kubernetes cluster, which runs the same script for doing model quantization using the Snapdragon Neural Processing SDK. when you log into the Qualcomm Developer Network, you'll be able to download that neural processing SDK from this website. You'll also need to download the Linux version of the Android NDK. I've downloaded both of those here in my hard drive already. We've tested this with the Snapdragon SDK version 2.5. In the previous video, I talked about this Kubernetes cluster, which is going to run quantization workloads in an SNPE namespace, where that quantizer is going to be doing quantization of our Snapdragon models in the cloud here. The setup for all of that is done in the Docker quantizer folder, where there's a Docker file for setting up the Snapdragon SDK, the Android NDK, and a bunch of other things that we need to run the quantization jobs in the cloud here. This will actually populate a deployment script for deploying that quantizer to your Kubernetes cluster from an Azure container registry with horizontal auto scaling, which will scale up to do lots of quantizations in parallel to reduce the total time it takes to quantize all of our models. There's a PowerShell script in here that will create some of these Azure resources, including the Kubernetes cluster, an Azure storage account, and then it will give you the Docker commands that you need to run the Docker build. So if I go into the AML Docker quantizer folder, I can run PowerShell. I already have some environment variables set up for the SNPE SDK. I will need a variable for the Android NDK, and these files need to be here. And lastly, I need an input test set as a zip file, because this is also going to be copied to those pods in the cloud. This test set is used because the quantizer is a data-driven quantizer and it needs some sample images. I've already created 10,000 images in the zip file here. You don't need the full training data set, of course. So now I can run the setup script, and it's checking to make sure I've got the right Azure subscription. I'm actually going to use a different storage account, so ignore that. And this is creating a storage account, it's creating a container registry and the Kubernetes cluster. It's configuring my local Kubernetes cluster so it can talk to the Azure Kubernetes cluster. I've already done that. It's uploading the dataset to a blob store, and now it gives me the Docker build command line, which will be needed to build that Docker image. You can actually do this on Windows if you have the Docker desktops installed, set up to use Linux containers. I've already done that, but you can tag the image with a version number. The version number you'll find in your quantizer.yaml file, which is generated from this template with the model storage connection string filled in. The version number here will be automatically incremented based on what's already in your container registry. This one has found version 1.32, so I'm going to tag the new image with that number, and then I'm going to push it using this command here. So then the container registry will be set up with the Docker image we need to run on our Kubernetes cluster. You can then deploy the quantizer with the horizontal scaling to your Kubernetes cluster using this command here. I've done one extra thing for simplicity, which is I've defined a default namespace to be SNPE, and that way my kubectl get pods is able to find the namespace SNP. Otherwise you'd have to do this on every command line. You can see that there's a pod running. You can also check that the pod is running the right version by looking at the description of this pod. Early on here we should see the image version number 1.31, which is correct. So this is good to go. So the Kubernetes cluster is now ready and waiting for work to quantize models in the cloud. The Azure ML workspace is already set up. The only thing you need to do is create that workspace and set a command line argument that points to the resource group and the workspace name, and then the AML script will be able to find it. You can now run aml.py to kick off a search job. And then everything in this diagram will start behaving, and the quantization and Qualcomm device testing will happen. And you can check the Azure storage table to make sure all of that stuff is working. If you go to the storage browser, open up the table, you can see here that a bunch of models have been defined by this search already, and because it has mean inference times, it means that the Qualcomm hardware inference testing has already been done. You'll notice that the inference tester actually does 5 separate benchmark tests to get a mean to make sure that, and make sure the standard deviation is low. If the standard deviation numbers come in too big here, then you're getting too much variation across your Qualcomm hardware devices. But these numbers look pretty stable. That's great. And you can also see that there is validation numbers here also coming from partial model training. So these models have been fully processed. We can obviously do that same trick to say what status is not complete to see what's currently happening. So there's two models. One of them is being trained, and that's what we're waiting for. If we go to the pipelines here, we can see that those training jobs are running. There's only two training jobs here because all of the other ones were already finished. Where are they at? 80%, so they should be finished soon. My Linux machine that is connected to Qualcomm hardware is over here, and I can see all the Qualcomm boards that are connected. And we have some remote screens running. And each one of these is running that runner script. This runner script is not doing anything. Let me just kill that so that we can, I'll kill both of them, so that we can see how to set this up. So I have on this Linux machine a copy of the Archai repo, and I can go into the tasks, face segmentation AML folder. There's a script there which will show you how to launch each one of the runner scripts for each Qualcomm device. It creates separate experiment folders, 1, 2, 3, 4, for each one of those devices. And so if I run this command line here, it will start the running script in a screen that's detached for that Qualcomm device, and it will say don't do any quantization here because we're going to do quantization in the cloud. I'll set that one up. I'm also going to set up this one. You may need to make that shell script executable. And now they're both running, and we should see this here waiting in an idle loop for inference testing work to be done. Control AD will detach that remote screen. Remote screen is handy because if I exit this SSH connection, it will keep running in the background. So that's how to set up this remote inference testing, and I've shown you how to set up the Kubernetes cluster for quantization. We already have the AML workspace set up for running the partial training pipelines, and everything is good to go.